we are going to discuss section 4, which is on interference of transmitted light through double slits. So basically, we are going to have an opaque board in which we have two slits. Now, if we send light through to the board, what will happen is there will be light wave emerging from the two slits that we have created. So there will be two light wave emerging from the double slits, and they will overlap in the same region. So in this section, we are going to discuss the behavior of the interference or the behavior of the overlap in that region, and we'll discuss what kind of pattern can we see if we have light emerging out from these double slits over here. So to understand the idea of what will happen to the interference of the light wave transmitted through double slits, maybe we need to recall something that we have learned from the previous semester when we are discussing about standing wave. Okay, so when we are discussing standing wave from the chapter on mechanical and sound wave, we learned that when we have two or more waves overlap, interference will occur. Okay, so interference is the requirement that you need to create a standing wave, and that is what we learn when we are talking about standing wave, in which if we have a traveling wave, one traveling to the right, one traveling to the left, when they arrive in the same region, they will overlap with each other, right? When the two waves overlap in the same region, there will be a phenomenon that will occur, and that phenomenon is called as interference. Okay, so this is what you can see over here. When the two waves arrive at the same region, the way they overlap, we call it as interference, and we are going to study this behavior when it comes to light wave passing through a double slit. Okay, so you can see this kind of interference happening in various situations. So here is a musical instrument, and you can see there's standing wave being produced on the guitar string over here. So that's one particular popular example of where we can see standing wave. Or you can see in this example over here, in which a person here is oscillating a slinky spring. So when you are oscillating a slinky spring, you are sending traveling wave to the right. But let's say if you fix the position of the slinky spring to a wall, what happens is the wave will also reflect back towards the left as well. So the wave that you send to the right and the reflected wave that is going to the left, and they overlap in the same region, they will undergo interference. So this phenomenon will occur in which they interfere with each other, and the resulting pattern is what we see here as standing wave. Okay, if you wish to know more about the idea of interference on this kind of physical strings or in air, you can talk about it. You can review the playlist that we have on standing wave. But now I'm going to talk about to be more focused on the idea of the interference itself. Okay, so interference occurs when we have two or more waves overlap, but the resultant wave pattern is determined by the principle of superposition of wave. To understand how will the resultant pattern be, whether it be a larger wave or you cancel each other out, to predict what kind of wave pattern will be formed, we will be using the principle of superposition of wave. So principle of superposition of wave says that when two or more waves are moving in the same region, the resultant displacement at any point is the vector sum of displacement by each individual wave at that point. Okay, so two or more waves in the same region. So let's say here you have source 1 and source 2. So source 1 will produce its own light wave, source 2 will also have its own light wave. But let's say you're interested with the resultant displacement or the resultant combination of the two waves at point B. If you are interested with how will the resultant wave be like at point B, what you can do is you can take the displacement of the wave produced by source 1 or state 1. Okay, so here you can see that the displacement of the wave produced by source 1 at B, you can see that at this point the wave is arriving at B with the equilibrium. Okay, you can see it's peak, equilibrium, trough, equilibrium, peak, equilibrium, trough. Then you reach there, it will be equilibrium, peak, equilibrium, trough, equilibrium. So the light coming out from source 1, when it arrives at B, it arrives at the equilibrium. So Y for source 1 is equal to 0. Y is the displacement. The displacement for source 1, light source 1, is 0. For source 2, you can see that it arrives at trough, equilibrium, peak, equilibrium, trough, equilibrium. So you can see that both of these waves, they arrive with displacement equals to 0. So y for source 1 is 0, y for source 2 is 0. So if you add them up, you get 0 as well. So that's why at this particular moment, the resultant displacement that you will see at point B will be equal to 0. Okay, now that's the idea of principle of superposition of wave. Okay, but the main reason why I recall this principle of superposition of wave, because this idea tells us that in this region over here, you find certain point which behaves in a way that the way they interfere will always resultant in maximum crest, maximum trough. It will be an enlarged or a wave that is much larger than before. At certain other points in the region, you also find points where in which after the two waves overlap, right, you see nearly nothing. Okay, because the two waves actually cancel out at those points. So you see points in which there will be constructive interference, and you see points in which there will be destructive interference. So the diagram on the left here is actually showing a constructive interference, even though we say that it sums out to be 0, but it's only 0 at that particular moment. Let's see what happens later. What happens later is the trough for light source 1 will reach B, and the trough for light source 2 will also reach B. So trough meets trough. If you add them up, you get a bigger trough. Trough that is 2 times larger. Then later, after that, you will see peak of light source 1 reach B. You will see peak of light source B reach B. So it will be peak meets peak. So it will be a peak twice the size. So it's trough meets trough, peak meets peak, trough meets trough, peak meets peak. So this kind of situation where the two waves arrive at the point in phase, they are arriving with the same phase. This kind of situation, we call it as constructive interference, because if you add the two waves up, you always get a trough that is maximized, you always get the crest that is maximized as well. So the whole wave actually becomes enlarged, or it becomes larger, the largest possible, you get the largest possible resultant wave at this kind of point over here. Okay, on the diagram on the right, you see point C here. You can see that the wave from light source 1 arrives at point C with a crest. The wave from light source 2 arrives at point C with a trough. So this one is a crest meet trough situation. So crest is the maximum positive displacement, trough is the maximum negative displacement. So they will just cancel each other out. So what you see here at point C is it will be positive amplitude plus negative amplitude, so you get a resultant displacement to be equal to 0. But you can say this thing will happen throughout the whole experiment, because later on you will see peak meets trough, you will see trough meets peak, you will see peak meets trough, you will see trough meets peak. So it's always, they are always anti-phase. Okay, the phase relationship is always opposite to each other. So when this one is maximum, this one will be, but when this one is positive maximum, this one will be negative maximum. Then they'll cancel out. Later on, it will be this one negative maximum, this one positive maximum, also cancel out. So it always cancel out to become 0. So for this kind of point, we see a destructive interference happens, or you can say that the two waves interfere in the destructive manner in which they will cancel each other out. So you see very minimal or nearly 0 resultant displacement over here all the time. For constructive interference, as the word constructive says, they will overlap in a way that they will enhance each other. So it's peak meets peak, so it becomes an enhanced peak. Trough meets trough, it becomes an enhanced trough. Okay, so that's the basic idea of constructive interference and destructive interference. So later we'll see if we have two slits and we have light passes through it, the two light waves will basically overlap in the same region, and we will try to determine at which point we'll see constructive interference, at which point you'll see destructive interference, and that will result in what kind of pattern if you place a screen to see what the light to observe the light that will fall onto the screen, what kind of pattern will it form. Okay, so that's for the next video.